Hi viewers, welcome to today's lecture on soil fundamentals. You're here to subscribe to our channel. Please do so and hit the bell icon to get notification on our new videos. My name is Engineer Namdi. So today we'll start with, we'll need to define some quantity variations, because under normal circumstance, when a soil is undisturbed or it has not been touched, we are talking about its bank volume or bank measure volume or bank cubic meter. So but when we lose the soil or try to excavate the soil, it is now referred to as loose measure or loose cubic meter. But by the time you start excavating the soil is now in a loose form, and it is referred to or estimated in loose measure or loose cubic meter. But when you try to fill up the soil and compact it, it is now expressed in fill or compacted volume. So today we are going to illustrate this with examples. We're going to perform some calculations to be able to illustrate what we are talking about. I have the first sample here. Call this soil A, and this is soil B. I will call this soil C. Soil samples. This one is A. Call this A. I will call this B. Call this C. So these soils we are talking about are with the same volume, the same mass. Let's say mass of 1,200 kilogram. Second one 1,200 kilogram. The third one is still the same with the same mass, which is 1,200 kilogram. So but when this same soil of the same mass in its bank measure, that is undisturbed form, call it bank measure. So let's say the volume then is 1 cubic meter or 1 meter cube. So by the time we lose it or we try to excavate the soil in its loose form or loose measure, call it loose measure, the soil is expected to have, or the volume is supposed to have increased, because of by the time you lose it, you are trying to introduce, or you're going to introduce air. So air will diffuse into the pores of the soil. So then we expect to have a higher volume. So we may have something greater than 1 cubic meter, which, let's say for instance 1.25 cubic meter, 1.25 cubic meter. Then by the time we start compacting the same soil, by the time we compact this soil, applying compaction methods, we don't expect to have same volume. We cannot have the same volume, the original volume we achieved before. So in the third case, which is C, we'll be having compacted, we'll call this one compacted volume. So we expect to have a decrease in volume, but with the same mass. So we may be compacting, and doing compaction we may achieve a lower volume, let's say 0.75 cubic meter. So we're trying to illustrate the nature of soil in its bank, loose or compacted state. So when it is in a bank measure or bank original form, it has the same mass but with a 1 cubic meter. Then when it is loosened or doing excavation, we expect that we are trying to loosen the particles of the soil and air may be introduced So this will increase the volume of the soil, but with the same mass. Then when we now compact the soil, or we bring it to the point of use and start compacting, we expect that the volume will decrease. So we've illustrated this, the same mass for the 3 states, but different volumes. So the next thing we have to look at is swell and shrinkage. Swell and shrinkage of soil. So when we talk about swell, we said this is the increase in volume over the natural or in situ state. So when we are trying to illustrate this, we said mathematically it is best calculated by taking the ratio of the difference in unit weight of the natural and loose materials to the unit weight of the loose material. So we are going to, for us to get our percentage swell, we will illustrate this using the formula. We say percentage swell, we're expecting swell in percentage, which is denoted by SW, will be equal to, we said, weight of bank measure in cubic meter or cubic feet, depending on what we're using, over weight of loose soil, so in cubic meter. Then we minus 1, close the bracket, and we multiply by 1000. So that will give us percentage swell. Weight of bank, that is soil in its original form, over weight of the loose minus 1 times 100. Or we can also express this as, 1 over load factor, minus 1 in bracket, multiply by 100. So we're expressing it in percentage. So that is our percentage swell. The next thing we'll look at is shrinkage. When a soil undergoes or changes from its natural state to the compacted state by taking the ratio of the difference between the unit weight of the compacted and the natural material to the unit weight of the compacted soil. So what we are saying here is that shrinkage in percentage, is a reduction in volume when a soil changes from its original state to the compacted state. So shrinkage, which is denoted by S subscript H, is equal to, we have 1 minus, we open another bracket, the original weight, which is bank weight in cubic meter, over loose weight, loose in cubic meter also, cubic meter, minus 1, we close the bracket, and we multiply by 100. By multiplying by 100, we are expressing it in percentage. So we can also describe other quantity variations that are related to shrinkage. Here we have load or swell factor. Say it is equal to the loose density over bank density. It's given by the ratio of the loose density in kilogram per cubic meter over bank density. Both is in kilogram per cubic meter. So shrinkage factor is equal to the bank density over compacted density. The original density over the compacted, when it is compact, the soil is compacted density, and is in kilogram per meter cube, So that's what we have. So the next thing we are going to look at is spoil banks. So when we are planning and estimating earthwork, so it is necessary for us to determine the size of pile of material that will be created by, or when the material is removed from the excavated point, and also is being heaped or kept at the point of use. So if the pile of material is long in relation to its width, it is referred to as a spoil bank. So a spoil bank is usually characterized by a triangular section. So it can be in form of a triangular shape or a conical shape. So in this case, we have to be able to determine the spoil bank, or the triangular spoil bank or conical spoil bank. We need to have in mind the angle of repose. A triangular, we say triangular spoil bank, Here we have the volume is equal to the section by the length for a triangular spoil bank. So its volume will be equal to the section multiplied by the length of the bank. So where we have is given by a formula B bracket 4V over length times tan R raised to power 1 over 2. So here we can say H, where H, or the height of the spoil bank or pile, is equal to B times tan R over 2. So from this calculation, or from this formula, B is where B is equal to the base width. This can be in meters or in feet. Then H is the height of the pile or pile height, also in feet or meters, whichever one, feet or meters. Then the next thing we need to consider also is the L, which is the pile length. L is equal to pile length, and the R is the angle of repose, which is in degrees. We have the R is equal to the angle of repose, which is in degrees. Okay, so the V is the last parameter we have here, which is V. V is equal to pile volume. So V is pile volume. The V is equal to volume of pile. So this formula here, we said section by length. Here where we have the B is the, we said is base width. The V, we have our V is equal to the volume of the pile. So but this particular volume is different from the smaller volume we are having here. This is the volume of pile, while this is the total volume of the triangular spoil bank. This one is the volume of the pile. Then here is the length of the pile. Then we have R, which is to say is the angle of repose. H is the height of the pile. For a conical spoil pile, conical spoil pile, for a cone, you know that the volume of a cone is equal to 1/3 multiplied by the area or base area, the base times height, base times the height mathematically. So with this, we'll be having, using the formula, D is equal to 7.64 V over tan R, where R is the angle of repose, over what, that is raised to power 1/3. So where our H is equal to D over 2 multiplied by our tan, the angle of repose. So here the D is the diameter of the pi base, which can be in feet, where D is equal to the diameter of the pi base. It can be in feet or in meter. So we will take an example based on this. We take an example 1 for a triangular spoil bank. Triangular spoil bank. Okay. So here we're asked to find the base width and height of a triangular spoil bank containing. The triangular spoil bank contains 100 BCY, which is the equivalent is 76.5 BCM bank per cubic meter. If the pile length is given as 30 feet, pile length is 30 feet, which is 9.14 meter, and the angle of repose, soil angle of repose, is 37 degrees, and we are given a swell of 25%. So what do we need to do? We first of all calculate the loose volume. To solve this, we call this solution. We said loose volume. We first of all get its loose volume. This will be equal to, here we are given that, so we have to multiply the 27. We use 27 to convert in feet. So 27 multiplied by 100, we are given 100 BCY, multiplied by 25% is, then you divide this by 100, so it is something as 1.25, 25% of it, because when you add 25% to 100%, 125, you divide by 100 to give you 1.25. So when we multiply this, we are supposed to have 375 cubic feet. So if we want to express this in cubic meters, we don't need to multiply by 27, we'll just multiply by 76.5, because it's given to us in bank per cubic meter, multiply by our angle, our swell percentage, which is still 1.25, and then this will give us 95.6 cubic meter. So that is what we have. We've been able to calculate the loose volume. Then the next thing we need to get is the base width, and the base width, we have the formula for the base width for a triangular spoil bank, where the base width B, let's wipe the top so that we can have enough, we have space to work with, have enough working space. So the base width, which is B, will be equal to, in bracket we have it as given earlier, 4V over the length times the angle of repose, tan angle of repose, okay, and then raised to power 1 over 2. So if we substitute into this, what we will have is we'll have a value of 4. This will be equal to 4 multiplied by, we've already gotten the volume in feet. We got it as 3375. So over, we have our length of the spoil bank was given to us as 30 feet. Remember, we're calculating in feet, multiplied by tan the angle of repose. The angle of repose was given to us as 37, tan 37. So we have this, we have to close the brackets, put it in bracket, then raise to power 1 over 2. So this, when you use your calculator to punch this, you have a value of 24.4 feet. So let us do the same thing in meters. When we are doing the same thing in meters, we use those values given to us in meters. Here we have our B is still equal to, substitute 4, the volume we got in meters is 95.6. So we say 4 times 95.6 over the length. What is the length given to us? We are given the length as 9.14. I've already wiped that off. 9.14 multiplied by tan the angle of repose still remain 37. So close our brackets, raised to power 1 over 2. We will have, when we use our calculator to punch this, we should have 7.45 meters. So that's what we have, meters. This is in feet, this one is in meters. The same formula expressed in feet and in meters respectively. So the next thing we have to calculate is the height of our triangular spoil bank, and to be able to do that, let's clean this so that we can have free working space or calculation space. So here we have, look at the height of our spoil bank from the formula we expressed earlier. We have, or we wrote earlier, we have that as B tan R over 2. So we'll do this in also in feet and also in meters. We already have our B already. So to do this for the feet, we have 24.4, which is this, tan, you know what our R is already, tan 37, which is the angle of repose, over 2. Divide this by 2. This will give us in feet, to give us 9.2 feet. And if we are doing that in meters, this will be equal to our B. We got B as 7.45 tan 37 degrees over 2. We do, if you express this, we are supposed to have this will be equal to, when we punch this out with our calculator, we should have 2.80. So that's what we have in meters. So close the bracket. So these are our equivalent in meters, and also the equivalent in feet as we've seen. Conical spoil bank. Let us do an example on conical spoil bank. Okay, so here we are asked to find the base diameter height of a conical spoil bank that will contain 100 BCY. So we are given 100 BCY cubic bank per cubic yard or equivalent of 76.5 BCM bank per cubic meter. So we have of excavation. If the soil angle is, as the angle of ripples is given as 32 degrees, and the swell is given as is equal to 12%. So what we need to do, we need to, just like we similar to what we did to in the case of the triangular spoil bank, the next thing we need to do is we calculate the loose volume. And in feet, what we need to do in feet is to multiply. In feet, we have to multiply 7. We use 27 because we are multiplying in feet times the 100 given to us in bank per cubic yard, multiply by the 12. Remember, we are given 12 swell of 12%. So 100% plus 12, that is 112. So when you divide this by 100, it will give you 1.12. So 1.12. So we are going to multiply by 1.12. So if we do this and multiply by 1.12, we'll have 324. Then in cubic feet, 324 cubic feet. So to do this in meters, this will be equal to 76.5 here, multiply by 1.12, and this will give us 85.7 meter cube. So we have this. If we multiply 76.5 by 1.12, then the next thing we need to calculate is the base diameter. The base diameter, and it is given to us to be equal to, here we have, it was given to us at 7.64 V over tan 32. Remember, if we recall to our initial, the formulas we wrote down. So if we substitute this, let us clean or wipe the top area so that we can have a space to do our calculation. So what we are going to have is, we will have 7.64. We are expressing it in cubic feet or in feet. We are expressing this in feet. So we have 7.64 multiplied by the volume. The loose volume we got is 3024. Then over tan 32. So we express it 1/3. When we use our calculator to multiply this, we should have 33.3 feet. So we do the same in meters. Doing the same in meters, we have 7.64 multiplied by, we had 85.7 over tan 32. This will be, we are supposed to multiply this, or we're supposed to raise it to power 3. So when we do this, we'll have use a calculator to multiply this by this and divide by tan 32. It will give us 10.16 meters. So in meters. So the next thing we need to calculate is the height. The height is given to us as h is equal to our b, which is the base diameter, over 2 tan angle of ripples. So in feet, we are going to have our base is 33.3 over 2 tan 32. times 32, and this will give us 10.4 feet. To express this in meter, it will be equal to, we got 10.16 over 2 times 32. This will be equal to 3.17 meter in meters.